Good morning, students. Today we have gathered here to go through the Euclid's division lemma or Euclid's division algorithm. In my last class, I explained what is Euclid's division lemma and what is Euclid's division algorithm. In order to refresh your memory, I would like to tell you that what is lemma and what is algorithm and what is the difference between the two. A proven fact used to prove some other problem is called lemma, and collection of some well-defined steps to solve a particular problem is called algorithm. In Euclid's division lemma, as I have told you, you must remember that when for every given two positive integers a and b, there exist two unique whole numbers p, q and r such that b equals to aq plus r, where a equals to bq plus r, where 0 smaller than equals to r smaller than b. For every positive integers a and b, there exists two unique whole numbers q and r such that a equals to bq plus r, where this value of r is the remainder, a is the dividend, b is the divisor, q is the quotient, and the value of r will lie in between 0 and b. Here we have written less than equal to sign. It means that the value of r can be equal to 0, or it can be more than 0. It can either be 0 or it can be more than 0, but in any case it must be less than b. This is actually Euclid's division lemma that I have explained in my last class. Now, regarding the application of Euclid's division lemma, I told you that this Euclid's division lemma is used to find out the HCF between the two numbers, and that process is known as the algorithm, division algorithm, Euclid's division algorithm. We divide, it is simply the long division methods. In each and every process we have to show by applying the Euclid's lemma. The second application of Euclid's division lemma we will go through today, and this question is, show that any positive integer is in the form of 2q and any positive odd integer is in the form of 2q plus 1. So we are going to discuss the next problem, and that problem is we have to show that every positive even integer is in the form of 2q and every positive odd integer is in the form of 2q plus 1. It has got a set rule. How we will solve it? Let's pay attention to the board. Let a be a positive integer. On dividing a by 2, we get q as quotient and r as remainder. Remember, this question is an application of Euclid's division lemma. Therefore, by Euclid's division lemma, we have a equals to 2q plus r, where 0 smaller than equals to r, smaller than 2, that is r equals to 0 comma 1. Now when r equals to 0, a equals to 2q plus 0, that is 2q, which is even as it is a multiple of 2. When r equals to 1, a equals to 2q plus 1, which is odd, as if 1 is added with an even number, the result is odd. Result is odd. Thus, we see, we can write over here, thus we see that every positive even integer is in the form of 2q, and every positive odd integer is in the form of 2q plus 1, where q is an integer. So this is the thing. How we will prove that 2q is an odd positive integer and 2q plus 1 is an odd positive integer, and 2q is even positive integer. You see, let a be a positive integer. On dividing a by 2, we get q as quotient and r as remainder. By Euclid's division lemma, we have a equals to 2q plus r. We have applied the Euclid's division lemma, and where 0 smaller than equals to r, smaller than 2, that is r, the value of r can be 0 and 1. Now, if the value of r equals to 0, a becomes 2q, which is even because it is a multiple of 2, and if r equals to 1, then a equals to 2q plus 1, which is odd, as if 1 is added with an even number, the result is odd. Thus we see that every positive even integer is in the form of 2q, and every positive odd integer is in the form of 2q plus 1. This is the question number 2 of your NCERT examples. Sorry, it is question number 2, yeah. Okay, now come to 3. Example 3 we will discuss now. Show that every positive odd integer, every positive odd integer, same type of question, will be in the form of 4q plus 1, and every positive even integer will be in the form of, every positive odd integer is in the form, the question says every positive odd integer is either in the form of 2q plus 1, 4q plus 1 or 4q plus 3. The question says we have to prove that every positive odd integer, either it will be in the form of 4q plus 1 or it will be in the form of 4q plus 3. In the same way we will start, we will write let a be a positive integer. See over here, we will write let a be a positive integer. On dividing a by 4 we will make it. See what change we are making, we will write it 4. Let a be a positive integer. On dividing A by 4, we get Q as quotient and R as remainder. By Euclid's division lemma, we have A equals to 4Q plus R, where 0 smaller than equals to R, smaller than 4, that is R can assume the values of 0, 1, 2 and 3. Now, when R equals to 0, A equals to 4 cube plus 0, that is 4 cube, which is even as it is a multiple of 2. When R equals to 1, the second remainder we are taking, when R equals to 1, A will be equals to 4 cube plus 1, which is odd, as if 1 is added with an even number, the result is odd. We have taken 2 remainders. Now the third remainder is 2. We will write when, let me write over here. Third case, when R equals to 2, we will write A equals to 4 cube plus 2. We will take 2 as common, 2 cube plus 1, which is even. And when R equals to 3, that is the last remainder we are taking, then A equals to 4 cube plus 3, or we can write 4 cube plus 2 plus 1, or we can write 2 cube plus 1 plus 1. This portion is even because it is a multiple of 2, and with it we have added 1. We can write it as 2m plus 1, where m is equal to 2 cube plus 1, an integer, and this A equals to 2m plus 1 is odd. So what we are proving here? We proved that any positive integer, any positive odd integer is either in the form of 4 cube plus 1 or it is in the form of 4 cube plus 3. Either it is in the form of 4 cube plus 1 or it is in the form of 4 cube plus 3. You see, if the remainder is R equals to 1, then the result is odd. If the remainder R equals to 0, the result is even. If the remainder R equals to 2, the result is again even. If the remainder R equals to 3, then the result is odd. Thus, any positive odd integer is either in the form of 4 cube plus 1 or 4 cube plus 3. Now, the next question we will see, it is a question where we will use the division algorithm. That means we are required to find out SCF. First understand the question. A sweet sailor has, question number 4 it is. The next question is, a sweet sailor has 420 Kaju Barfis. 420 Kaju Barfis are there and 130 Badam Barfis. 130 Badam Barfis. She wants to stack them in such a way that each stack has the same number and they take up least area of the tray. What is the number? What is the number of that can be placed in each stack for the purpose? Now see, the sweet sailor has got 420 Kaju Barfis and he is having 130 badam burfis, and she wants to arrange them in stacks, so that the condition is so that she wants to stack them in such a way that each stack has the same number and they take up the least area of tray. What is the number of that can be placed in each stack for this purpose. Okay. So our sweet sailor is having 420 kaju burfis and 130 badam burfis. One thing make it clear, my dear students, that number of stack cannot be more than 420 and 130. 130. So what we have to do? We have to find out the number of stacks, and the number of stacks will be smaller than 420 as well as smaller than 130. And that is possible if we take the HCF of these two. So simply HCF of 420 and 130 is the required answer. We will find it by the long division process, and then we will convert it in division algorithm. 420, 3, 0, 9, 3, 0, 30, 130, 4, 120, so this is the HCF is equal to HCF of these two numbers 420 and 130. We have got 10. So your final answer is the sweet sailor can make the stacks of 10 for both kinds of burfis. 10 stacks for both kind of burfis will solve the purpose, will be the answer of the question. Now this portion, as I told you earlier, this is actually the application of, this is the long division process. Now in standard 10, we are naming it as Euclid's division algorithm, which is a step-by-step procedure. The first step is this one, the second step is this one, and the third step is this one. So we can write step 1, 420 is equal to 130 into 3 plus 30. Step 2, 130 is equal to 30 into 4 plus 10. Step 3 equals to 30 is equal to 10 into 3 plus 0. Since the last remainder is equal to 0, therefore the last divisor equals to 10 is the required answer. Students, I hope that you have understood why we are taking HCF, when to take HCF and when to take LCM. That is the very important thing in this chapter. We will come across some more questions later on. To begin with, I have explained the 4 problems, and now you can easily solve the exercise 1.1 by yourself, and if you find any difficulty, we will have a discussion over it. So you please go through exercise 1.1 and do all the 5 sums given in the exercise. Thank you.